Welcome to another episode of the Corrosion Journal interview series. My name is Sammy Miles, the Managing Editor-in-Chief of Corrosion Journal, AMP's peer-reviewed scientific journal. Today's episode will discuss environment-induced crack initiation and early stages of crack growth in aluminum alloys, the topic of our January and August special sections. I'm joined by Henry Holroyd, a consultant, and Tim Burnett from the University of Manchester, who served as two of the guest editors for this collection. Thank you for joining me today.
Hi, Sammy. Thanks for asking us.
All right, so to get us started, can you tell us a little about yourselves for our listeners?
Okay, so hi everyone, my name's Tim Burnett. I'm a professor in materials and imaging here at the University of Manchester. I'm also director of the UK's National Research Facility in Lab X-ray Computed Tomography. And my background is a little bit interesting in that actually I did my PhD at the University of Leeds in the UK, but in multiferroic materials. And it was only in a subsequent job when I joined the University of Manchester in 2012 that I started doing research into environmentally assisted cracking and working alongside Henry, actually. The thing that stayed with me throughout all of my research is advanced characterization techniques, and that's something that I've applied to lots of different material systems and something that is like helping in my research today.
Hello, everyone. My name's Henry Holroyd. For the last 15 years, I've been a consultant retained by the company that formerly employed me. For the last 20 years, I've also been a visiting professor at Case Western Reserve University in Cleveland, and for the last 5 here at University of Manchester. I have to admit, I did my PhD 45 years ago with a guy called Redvers Parkins, who an ex-president of NACE, who's the grandfather of slow strain rate testing. And essentially, I've worked in industry and academia for the last 25 years, spending most of my time working on aluminium alloys.
Wonderful. Now, to start with, can you explain a little about what you mean by environment-induced cracking? What is that term more in layman's term? Yeah.
Well, in some ways, it's a catch-all. In the first paper we wrote in the review paper, we wrote in the January edition of Corrosion this year. The history goes back to the late 1890s, where phenomena such as spontaneous disintegration, seasoned cracking of aluminium, accelerated corrosion by stress. It was called different things, but essentially it was when you managed to produce subcritical cracking in something other than a vacuum. So you need a series of things to happen simultaneously. You need a microstructure that's susceptible. You need an environment that gives you the right type of attack, and you need the right stress conditions. It varies from different alloy to alloy what the best combination is, but we find some alloys will crack in water vapor, and they tend to be the stronger ones and the more modern ones. Those, for instance, would not crack particularly well in aggressive saline solutions. Several factors are important for initiation. So initiation is a subset of environment-sensitive fracture. And so we have concentrated in these two subsections on the initiation phase. So I hope that helps. It is many phenomena fit into environment-sensitive fracture. I mean, it can involve hydrogen brittlement. You know, it can be what people would call a no-dissolution cracking. So we came up with a term which we hope captured everything. And I know it didn't fit in exactly with corrosion, the journal's definition of this, and I think you call it environment-assisted cracking.
Mm-hmm.
Whereas,
yes.
You know, we forced the issue saying we want to call it this. So we deliberately did it because we wanted it to have a much wider meaning. So I hope that helps.
Yes. And You talk about initiation. What counts as the initiation stage or early stages of crack growth?
If I address this from two aspects, from a practical consideration, one could argue that the early stages of cracking is where it is only cosmetic. And in other words, it's not going to limit the performance of a structure or a product in real life. And I would argue that is something that we've learned to live with. Now, one can look at it from a science-based response, saying the early stages of cracking is when you get to a stage where that cracking will continue and would be a service issue. As you can see, I come more from the application of things as opposed to the raw science of it, which is why I work with Tim, of course. So I hope that gives you a feeling, because you can have cracking which is not going to be a problem in real life. But the purists would say you've been suffering environmentally sensitive cracking. But
right, it's not going to cause a failure.
Yeah, because otherwise, with aluminium aeroplanes, for instance, you'd say, well, we should have stuck with wood, because we know we have cracking issues, but we learn to live with them.
If I can add something to that, what I'd like to say is that the initiation is really that stage where you go from no cracking to cracking. So that nucleation of a crack, and that can form from different types of precursors, whether it is corrosion or really almost like a pristine surface. So, but really once we've got this nucleation of cracks, we've really gone from there not being a crack to there being a crack. And I think we can talk more later about the sort of challenges of that, but really it's been difficult to research historically, because that event of going from no crack to a crack can be almost instantaneous, and it's also happening at a very, very small scale. So we've got something very fast and very small, but actually that event of cracking initiation, nucleation, can take place after days, weeks, months, years. So how do you monitor, or how do you observe something very small and very fast that has got a delay built into it of a long time period?
And that's a perfect segue into what I was going to ask y'all next, which is, what are some of the challenges that researchers and practitioners have been facing with environment-induced cracking? So obviously, one would be, I would guess from the start, is just, when does it actually start? If it can be anywhere from days to years, right? That would be a challenge in itself to pinpoint it.
Well, you've hit the nail on the head in the sense that it's much easier to study crack propagation. And most of the published work out there is propagation based. And in our second set of papers in the August edition, we tried to encourage people to write about what have we been doing in terms of studying initiation per se. And if you go back to the 70s, people were really trying quite hard. Alcoa, there was a lot of government money around in those days, and they actually did some very detailed work. But people suddenly realized we don't have the tools to be able to really look at this at the level of magnification we need to. And it's only in the last decade, or perhaps in the last 5 years, we've had the experimental techniques that are allowing us to actually really study initiation. So there's a lot of potential advances we can make in understanding initiation. And one can argue that if a crack doesn't start, there's not a problem, because as we push materials, the industry is always wanting stronger, lighter materials, and we can get the toughness right. We can get the strength right, but more and more you find these cracking problems and secondary properties become challenged when you push materials. So we're now having to look at how can we get everything. We want our cake and eat it. So we need to study the very early stages, because we need to suppress that, because in some situations the growth rates are relatively high, which means you can't use that material. But the user's saying, no, look at the hydrogen economy. We're going to be needing lighter, stronger materials. And hence the recent advances, which I know Tim's going to talk about later, we're now in a position to really focus on what's happening in the early stages and nearly in real time as well, which is. I'm just hoping I'm around long enough to benefit from the work that comes out. Anyway, Tim could add to that.
Yeah, I think we're lucky that the number of characterization techniques that are available are really helping address this challenge. I think in addition to a lot of the electrochemical monitoring, which can be done at very high speeds, we need to add that understanding of the microstructure of the material. And I think what you find in this field is that we need to understand the fracture mechanics and the stress of the situation. And some people come at it very much from that perspective. Some people come at it very much from the electrochemistry aspect, and some people have come at it from the microstructural aspect. But really, you need all of those things together. So the latest characterization tools are allowing us to basically pull together observing microstructural changes in situ as we monitor, say, the chemistry that's evolving, and basically helping us understand those things that are building up to get this stage of initiation where we're actually forming a crack. And I think that is critical to have all of those things, all of those different pieces of information together. So some of the things that we could do more specifically is that if we use imaging, either in the optically or very high resolution optical imaging or X-ray imaging, we can actually still have realistic environments to do testing under, but we can see changes to the microstructure that are taking place, and then put that in context with electrochemical measurements. So we've really got a good idea of all those things that are changing once you take a material, you apply a stress to it, and you expose it to the environment. There's changes taking place at a very, very subtle scale over a period of time, and we need to understand that before we then go, right, and now it started cracking, because that doesn't happen instantaneously. There's something changing about the material when it's introduced to those different conditions.
On top of what Tim's just said, a lot of current test methods really don't use the same surface conditions that are used in real life. So we've got to pay a lot more attention. If we talk about initiation, we've got to mimic real life simulated conditions. Plus, the environments that we use have to be relative to the application. I mean, we've had problems recently in advanced aluminium alloys used in aircraft, where you tick the box saying, well, we passed ASTM G46 or whatever it is, but that's testing it in alternative immersion sodium chloride, which the material does okay in. Doesn't do well in slightly elevated temperature water vapor. So there needs to be a moving of the times where we ensure with new applications, but also you've got additive manufactured materials coming in, which we don't have the same history base, knowledge base on how these are performing. And to say, well, we'll just use the tests we used to use over there. Well, some of those tests aren't working too well with some of the latest materials, let alone on additive manufacturing. So I'm hoping that we're going to have a group of people wanting a serious conference on initiation, because we need the meeting of the minds of saying, well, what's the best way forward? Because we're honoured with all these testing techniques, but the testing techniques are no good if you're not looking at the right thing. So.
Right. If you're not in the right environment, for example, if the real world conditions don't match, then that does become a big challenge and a big problem.
At least
really.
aren't related. I mean, I'm not saying you have to
Mm-hmm.
mimic exactly, because it's the classic dilemma with testing. You need to somehow accelerate things so it happens rather than waiting. Some of these materials can take many years to get to this point. we need something that's going to work in a realistic timescale. But we can't throw the baby out with the bathwater, which I'm afraid has been happening in more recent times. We've pushed some materials past the point where conventional testing is going to give you the right answer. And that's, it's a view that's beginning to percolate up, I hope.
So with that, and I might already know the answer to this, but can we predict where cracking will occur? Are there any situations where we can say, yes, we think it's going to happen in this spot or maybe at this time range?
Absolutely, but at the design stage, we're meant to rule those out. Quite often what is happening is you can test the material on its own. Now, if you then say, well, I'm insisting having this aluminium alloy and I'm going to couple it with this material, and you start getting galvanic effects, you can say there's a higher likelihood of problems somewhere in that interface. And I know, for instance, Rob Kelly and people at UVA do a lot of work on that. So, the answer to your question is yes, we can, but there seem to be several combinations you can come up with that can give you problems you haven't necessarily anticipated. And that's the scare, because we can't get it right all the time, it would appear.
I think one of the interesting things as well is that actually when we do a post-mortem investigation on the initiation, we can actually have a pretty good understanding of why that site was the site to initiate a crack. So actually, with that information, in theory, you could predict where initiation was going to occur and maybe something about how long it was going to take. But the issue is that actually the microstructure is a scale of micrometers or even down to nanoscale features, and you've got meters and square meters, hundreds of square meters, maybe in an aircraft, where you actually have to resort to more stochastic approach to predict initiation times and initiation locations, because you can't take into account that vast area of the material. So which are going to be the most likely locations? So we're forced to adopt a stochastic approach to have a practical way of predicting. But interestingly, now we've got enough detail about these sites, we can actually understand why failure initiated in certain locations, but we can't really put those two things together because we can't include the whole diversity of the features that you might find across huge areas of surface that are available in large structures.
So what are some of the recent advances in understanding, detecting, and preventing environment-induced cracking in aluminum alloys? I know Henry said you'd be talking about advances later, so here we are.
Well, if we look at the latest generation high-strength alloys, one can argue we stretched the rubber band to the point where to move to another new generation, it needs an innovation. So we can, if you like, improve what we've got, but I wouldn't be allowed to tell you if I knew. But so obviously alloy development, one has hope, but a lot of iterations and opportunities have already been exhausted for the high strength 7000 series alloys. Now it may be clever things with rare earths, clever things with thermomechanical treatments. We can move forward, but at the moment I don't see a step function change. Now it is interesting. Some of these more recent developments with additive manufacturing, that their microstructure is different. And the jury is out at the moment about how susceptible these materials are. And I don't think it's going to be like Henry Ford, because when you design cars early on, you'd put something out, and if something fell off, you'd say, oh, we've got to try something different. In other words, we need to be more selective than that. So I don't think that there's an answer in terms of alloy development, other than something clever that comes out of additive manufacturing or other alternative casting techniques. I don't see a new magic alloy system that's going to come in. There's no, it's not like aluminium methyl alloys 20 years ago. Suddenly we're going to save our life.
I think in the first review article, looking back over the development of aluminium alloys, we were able to show that actually, if you have like a 7000 series alloy, so with the additions of zinc and magnesium, there seems to be, so you add the zinc and the magnesium to have a higher strength material because you need more of the precipitates to form. But you reach a limit essentially to how much zinc, magnesium you can add to the alloy before you really just run straight into this issue of environmentally assisted cracking. And it's interesting that you can add different alloying additions to actually get a little bit further. So then keep a higher zinc and magnesium content and then actually still have good performance from your material. But we've maybe reached the limit, and it's a bit of a shame really that actually the highest strength materials that we can make are actually some of the very most susceptible to this phenomenon. But I think there is a lot of work at the moment to look at different heat treatment processes, which do again help improve that. But again, we think there's a limited potential to really take this system and sort of take it into a regime where like environmentally assisted cracking isn't a problem. And I think, still, again, what is difficult is that we have to go back a step with a lot of our investigations to understand the materials on a sort of more fundamental basis in terms of their microstructure and properties, to then understand the mechanisms, to then mitigate against those processes to have a better performance. So, and that each time you get an advance in the characterization techniques that you've got to be able to get better information, and a lot with modeling to actually be able to explore lots of the different compositions and heat treatments. Again, you have to, each time you get an advance in those techniques, you have to sort of go through that process to make sure you understand what's going on. And I think it's only when you get that understanding that you can then try and apply that to avoid that initiation scenario or this propagation scenario. And that means doing quite a lot of work, going back through and making sure you really understand what you've got.
And unfortunately, the user is never satisfied, because you move the window we can operate in up a bit, and then they'll want to go further. So, I think we have an opportunity, as we said earlier, but because we can now actually really almost in real time see what's happening, you can learn a lot. And some of the things that we have assumed are not necessarily 100% correct. They need modifying. So, there's hope. But I also think that there are opportunities in terms of monitoring in real life, where we can have smart systems, because you don't necessarily need to know exactly where the problem is. If you're in a structure, you just need to know you've got a problem. Sometimes, we don't need to know, well, it's actually located exactly there. If we just know in this region here, we've got a problem, you then know where to look. Because earlier on you say, do we know exactly where it's going to occur? Around a well, yeah, you've got an idea. Around a joint, but if it's occurring in an extrusion or plate away from there, you don't really know. And some of these structures are large, so
Right.
ships, we had a problem. In planes, there are some UK trains we've got a problem at the moment, and it's stress corrosion related, or I should say environment.
So you just touched on a couple of them, but what are some of the areas that we still need additional research in? Obviously, you've touched on some of the techniques and trying to get those.
Well, you can push me into an area which you could say is something. I believe we were talking about cosmetic cracking right at the beginning. I believe some of these high strength materials can start cracking, but the cracking arrests, and that's it, right? And so we need to know more about that. Why in some alloys we can get cracks that clearly have started, and we can start them in the lab, but they're not a service problem because for some reason they've arrested. So we need to start understanding, well, what's causing that arrest, and then you build that into stronger and stronger alloys. So you actually live with the fact that, well, this phenomenon is going to occur, but we know it's not going to become an issue. So rather than saying you've got to have something that's absolutely free of the phenomena, we've pushed some of these systems so far we can't have that. So we now have to fall back on another line of defense to say, well, we'll have a little, but it's not going to cause us a problem. We can be slightly pregnant.
I think some of the really valuable things that we've learned recently is that there is like clearly different stages of initiation in terms of that very initial nucleation of a crack, but then actually the short crack behavior or small crack behavior where the crack is smaller than like a grain of the material, and then when the crack is longer it actually has a different behavior. Actually just us understanding that better is, again, there's new opportunity to investigate and potentially interrupt some of these processes. And then you could look to like surface treatments and things like that, which specifically are trying to counteract that mechanism. I think one of the real challenges that still remains, though, as well as needing to just do a lot more work on initiation in general, is that when you consider like an in-service scenario, the diversity of the environment is often really like difficult to track, especially when you think about aircraft and like things in ambient environment where the temperature can change drastically, or the humidity, or it can get wet and dry. All of these things really make it very, very difficult to see what effect long-term will that have on initiation, what effect long-term will that have on propagation. I think the other aspect of that, and again, most research doesn't get very close to doing this at the moment, is that we do a study on a material in the lab, and we might have a very, very good test, which is realistic environment, etc. But actually, when you integrate that material into a complete structure, you know, it's joined, it's coupled with other material, it's got a slightly different surface finish, it's got a coating system on it. So we talk of this complete stack up in terms of how that is integrated into a whole, you know, aircraft or a whole ship or a whole car. And actually, you've got a very different scenario. You add on to that this very diverse like set of environments that it will encounter during its lifetime. And you sort of start thinking, how can we possibly like cover all of those bases? So actually having really clever ways of monitoring like in-service scenarios in terms of like the temperatures, the humidity, the like environment, and also the stresses and things like that, and putting that together with a program of like testing and investigations into materials that starts to get towards that is like ultimately what is needed. But you hope we can use a lot of sophisticated modeling to help identify those things that are going to be the most important things, that are the really primary factors that are going to affect lifetime of a structure, to really target the research in a sensible area, because you can't really account for the entire complexity. That's just when you've got a final product and it's doing its job, and then you learn something from that. But hopefully you're not relying exclusively on that to get the information you need.
Now, one thing we've not talked about with initiation, it's about initiation of what? Because the very early stages, and I know you've had another podcast on pit to crack transition. right? So what are we actually talking about now? Where I'd be coming from, it's a transition from something that's cosmetic to something that's going to cause a problem. And we need to understand what's happening in the very early stages while it remains cosmetic. And there is some, experimental evidence that the activation energies controlling the very early stages are different to the later stages. So crack propagation is actually controlled potentially by something that's different. So we need to get a better feel on what's controlling the very early stages. By understanding that, we may be able to live with the fact we'll have some of that, but it's never going to move into that. So in other words, you can call it pit to crack transition, but we prevent that transition of the phenomena. So when we say initiation, it's a spectrum of things going from something which is, literally the very, very first thing that happens on the surface through to something that may be happening 10 microns below or 50 microns below. But most people know with aluminium alloys, generally surfaces, the first micron or so is a disturbed layer, very different microstructure to the bulk. Not a lot of work has really been done on studying what's happening very, very early on in that region there. And that can be the difference, because if it doesn't start, it's not going to propagate. And we then end up with the possibility, well, we're already doing it, using materials we know that can crack millimeters per year, but we've been using them in critical applications and not had problems with them because it's never started. But if it did, you're in trouble.
If it did, it would be catastrophic. But as long as you can prevent it.
And there have been examples of that, yeah. And yet we've got the crack propagation ASTM test methods that tell us, oh, that's what that material does in that environment. And yet we can tick the box because we got practical experience that says, oh, no, we've not had a problem for 20 years. So, for new materials where you don't have that background, you say, well, is this one going to be okay? So there's plenty of scope for young people wanting to get into this field.
There's always place for new research.
Absolutely.
Wonderful. Well, thank you both for joining me today. Before we wrap up, if people want to get in touch with you later, what's the best way for them to reach you?
Yeah, I think hopefully people can find me easily if they put in my name, Tim Burnett at Manchester. You come up with the my Manchester profile, and there's like contact details on there.
And with me, the easiest is just email henry.holroyd @ and then it's luxfer.com, luxfer.com.
Perfect. And for those listeners who want to learn more about environment-induced crack initiation and aluminum alloys, please go to corrosionjournal.org and read our January and August issues. You can also search our website for additional articles because we've published a number over the years. And with that, I'm Sammy Miles here with Henry Holroyd and Tim Burnett. And thank you for listening to another episode of Corrosion Journal's interview series. You can subscribe to AMP Podcasts if you haven't already on Apple, Google, Spotify, and all the major distributors. If you want to learn more about the journal, make sure to visit corrosionjournal.org. You can find all episodes of AMP Podcasts on amp.org. That is ampp.org. We'll be back soon with another episode. Thanks for listening.